section, 9.6, we're going to look at what are called alternating series. So an example of an alternating series would be the alternating harmonic series. So we looked at harmonic series back in section 9.4. And in that series what we had was 1 over k as the rule for creating that infinite series from k equaled 1 to k equaled infinity. And in order to make that alternating, in order for the signs to alternate between positive and negative, what we'll do is we'll make the numerator -1 to the k plus 1 power. So think about taking -1 and raising it to different powers. Your only possible outcomes are going to be either +1 if the power is even, or -1 if the power is odd. So it's not really going to change the value of the numerator, it's just going to alternate it between -1 and +1 as the power alternates between an odd and even number. So this specific infinite series will look as follows. So if I let k equal 1, then my numerator will be -1 squared, which is going to be +1, and then of course my denominator is also +1. So my first term is 1, and then to it I'm going to add, when k equals 2, I get -1 cubed, so that gives me -1 over 2. And then when k equals 3, I'm back to a positive numerator of 1. And when k equals 4, I'm back to a negative. So you can see here that what I have are these alternating terms, or alternating signs every other term. So here I had a plus, a negative, but obviously that's just subtraction. But we have a positive, a negative, a positive, a negative, and so on. So that's what we refer to as an alternating series. So we are going to look at what's called the alternating series test. And there are a couple of conditions that need to be met in order for us to be able to use the alternating series test. So here are the conditions. Let's say we have some a sub k representing our infinite series. In order to make it alternating in sign, we'd have to multiply it by this -1 to the k plus 1 expression. So this represents any alternating series in general. And the conditions to use the alternating series test are, number 1, that the terms of the series are non-increasing in magnitude for, for k being greater than some n value. So the way that this is stated is a little bit unclear until you start actually doing some examples. But remember that non-increasing just means that it's either decreasing or remaining constant. So as you look at the terms of the sequence from one to the next, you want the values to be getting smaller and smaller or staying the same. You don't want them to be increasing. But the thing is that it's okay if it increases at first, as long as eventually down the line, for some n value somewhere, it's decreasing forever, or I should say non-increasing forever. So you're kind of thinking about the end behavior, and if the end behavior eventually has it so that every term is sequentially non-increasing after some arbitrary n value, then it meets that condition. So in order to test that, what we're going to do is we're going to be looking at some Calc 1 concepts where we take the first derivative and we set it equal to 0 in order to locate the critical values of the function. And then we will do sort of a test to see where the function f prime of x is increasing and where it's decreasing, and that will help us to make a conclusion about whether condition number 1 is met. So it might make more sense once we do several examples. The second condition that needs to be met is much easier, and that is that the limit of a sub k as k approaches infinity has to equal 0. So notice here the limit that we're taking leaves out the alternating sign piece. We are just going to be looking at the rest of the rule, the a sub k part, and we're going to look to see if its limit is 0. And if each of these conditions is met, then the conclusion that we must make is that this alternating series converges. Okay, so the alternating series test really gives us information about whether an alternating series converges. There is no mention about it diverging. So if we're unable to conclude that it converges by the alternating series test, then we might look at some other tests, possibly the kth term test or the divergence test, possibly the integral test, maybe some of the other ones from 9.5, ratio root comparison. You have many options, but again, to use the alternating series test, you want to make sure that each of these conditions is met. This pairs really nicely with the divergence test, because remember, in the divergence test, it's inconclusive if our limit equals 0. And so here, if the limit equals 0, with this test, we are able to come up with a conclusion. So they kind of pair nicely together. All right, so that's the rule in general. Well, let's take a look at some examples of using this test. My first example is going to be the infinite series, k starting at 0, going to infinity, -1 to the k power over 2k plus 1. Notice here that the alternating sign is written in a different form. It's not -1 to the k plus 1 as I had shown in this example up here. However, also note that the k is starting at 0 instead of starting at 1 like we often do. I'd like to just write out a couple of terms of this series just to convince you that it does represent an alternating series. So as k equals 0, remember anything to the 0 power is always 1, and in this case that's positive 1. Our denominator is also going to be 1, so our first term is 1. The second term, when k equals 1, gives us -1 to the 1 power. So there's my alternating sign, 1 over 3. K equals 2, I'm back to an even, so that's going to give me positive 1/5. K equals 3, I'm back to an odd, -1/7. So it's nice to look at a couple of terms just to convince yourself that what you are dealing with is an alternating series. However, in order to make a conclusion about whether this series converges or diverges, we might try the alternating series test, which means that we have to see if we are meeting these conditions that we need to meet. So the first question is, are the terms non-increasing and the magnitude piece here just refers to the absolute value of each term. So in other words, we're not talking about whether this is positive or negative in terms of bigger or smaller than one term and another. We're just looking at the magnitude, so the actual fraction or value itself regardless of the sign in front of it. So are the terms, the magnitude of the terms, increasing for some k value greater than or equal to n? And so as I mentioned above, what we're going to do is use some Calc 1 to figure out where this function, and by function here I'm referring to the function 1 over 2k plus 1, so regardless of the sign, where is this function increasing and where is it decreasing? And we are looking for non-increasing. So first thing I'm going to do is find the derivative of that function. Not L'Hopital's rule here, but the derivative. So since it's a quotient, we would use the quotient rule. So we have low d high, the derivative of 1 is 0, minus high d low over low, or low squared. Cleaning that up, my numerator is negative 2, and my denominator is 2k plus 1 squared. This is the derivative of my function. What I need now are some critical values that could potentially separate areas of increase and decrease. They could potentially represent minimums or maximums of my function, or points of inflection. So if I let this equal 0, remember critical values are values where the first derivative equals 0, or where the first derivative is undefined. So in terms of setting this equal to 0 and solving, there are no values that will make this entire fraction equal 0, but there are values where the function is undefined or where the denominator is going to equal 0. And specifically that happens at k equals negative 1/2. So this is our potential minimum, maximum, or inflection point. And so if you think back to Calc 1, we put that on the graph, and we can test either side of negative 1/2 to see if it's increasing or decreasing. And so what we're looking for is that the function is non-increasing or decreasing at some point after this critical value. So let's plug in a value to the right of negative 1/2. Let's say I use 0, that's a good value. Let's plug 0 into our derivative, and I'll get negative 2 over 2 times 0 is 0, plus 1 is 1, squared is 1. So in this case, I get a negative, which means that everything to the right of negative 1/2, everything bigger than negative 1/2, is going to be negative. Now let me just point out a notational error that I did make here. I said k greater than or equal to n, but there are scenarios such as this one where we can't have k equaling negative 1/2 because it's undefined there, but for everything larger than negative 1/2, our function is decreasing, which does fit the criteria that we are non-increasing. So all of that work allows us to conclude yes to the very first condition of the alternating series test. Yes, in the long run, the end behavior of this 1 over 2k plus 1 function is that it will be decreasing. Now, the second condition is that the limit of that function equals 0. So let's also find the limit as k approaches infinity of 1 over 2k plus 1. And I'll just keep reminding you here that we are really leaving the alternating sign piece off